Welcome back. The objectives of this video is to explore exponential growth and decay models, including things like half-life and a compound interest formula. So exponential growth and decay models will follow the format as we see here on the left. A of t equals a sub 0, or an original amount, times e, our base e, raised to the exponent k times t, where t is time and k is a constant representing a particular rate. If k is greater than 0, we will have growth, exponential growth, and if k is less than 0, then we will have decay. In example 8, we see that the atmospheric pressure P on a commercial airline decreases as the plane height increases. The pressure is measured in millimeters of mercury and is related to the height in kilometers above sea level. The relationship is modeled here as P of H equals 760 times E raised to the negative 0.145 H. Question A says, what is the atmospheric pressure at a height of 4.5 kilometers, about 3 miles above sea level? So we're going to find P of 4.5. We'll plug that in for H, and we'll just put that into our calculator. Question B asks the same thing, but they ask us to do that with an input of 10K, or 6.2 miles. So going to my calculator, I have 760, and then times E. E is above the natural log key, so second ln E raised to the negative 0.145 times 4.5. And we get 395.76. And then we repeat the process by putting in 10 for x. And we get 178.273. So I'll add those answers to the notes. Notice I'm working down the page, showing my inputs appropriately. In this example, we're going to look at half-lives or exponential decay, and we've seen in carbon dating that they use half-life to find the age of fossils up to 80,000 years old. This method is based on finding the percentage of carbon-14 in an item, and carbon-14 has a half-life of 5,715 years. So the half-life is the amount of time it takes the substance to decay to half of what its original amount was. So let's take a look at our half-life formula. If A of t equals a sub 0 times e to the kt, and remember t is time and k is some particular rate, and a sub 0, that's our original amount, or our amount at time 0. So if k is less than 0, then the half-life is going to equal the natural log of 2 over k. And I'll show you where the natural log key is on your calculator. Or, resolving that, k is equal to the natural life of 2 divided by the half-life. So, two formulas written differently, or the same formula really written differently. So, if we need our k is the natural log of 2, divided whatever half-life we're given. So here in example 9, we see the half-life of a certain radioactive substance is 24 years. So here we're given the half-life. So we've got the half-life is 24 years. A sample has 5.8 grams present initially. Well, that is our a sub 0. And they're asking us to write a model to express the amount of the substance remaining as a function of time t. So t is going to be our unknown. We have a sub 0, it's 5.8. But we don't have k. And remember, e is a constant, so we need to find k. So in order to find k, we'll use our natural log of 2 divided by the half-life. So K is equal to the natural log of 2 divided by our half-life of 24. Going over to our graphing calculator, we can input that into our calculator. So the natural log key here is just on the left-hand side. So the natural log of 2, and make sure you close your parentheses, and divide it by 24 gives us our K of 0.2888811. And then we can go ahead and substitute into our function a sub t equals our original amount of 5.8 grams times e raised to the 0.02888811 times t. And there is our function. When will there be less than 1 gram remaining? So when will it get down to 1 gram or less? So we want an output of 1, and put that into our formula, 5.8 e to the 0.02888811 t, and we need to solve for t. Well, we're going to have to use our graphing calculator to do this, so we need an appropriate window for x's and y's, and we'll need to put the formula into our calculator. So let's think about half-life. So if we have 5.8, cutting that in half then would be 2.9. So that would take 24 years because that's our half-life. And then to cut it in half again and get down to 1.45 would be another half-life. And to cut that in half again to get it down to 12.7 would be another half-life. So each of these half-lives is going to take 24 years. So 3 half-lives is going to be 20, 40, 60. That's 72 years at least, or almost, to get to that less than 1 gram remaining. So let's go ahead and find out exactly what this is by putting this in our calculator. But this 72 years is going to be helpful for us because that's going to tell us what our t's are. So we want to make sure our t's go at least from like 0 to 72. And of course our y's, since we only have 6 grams of material, our y's will just go from 0 to 6 when we set our window. So let's go ahead and put this into our calculator and see what we get. So I enter the formula into my calculator, the 5.8 e to our negative exponent times x, and then I've also graphed y equals 1, and we're going to find the intersection of these. First I'm going to set my window. Now remember our x's, we knew it would be about 72 years. I went out to 100, probably further than I needed to go. And then my y's, my amount of my material, we only had 5.8 grams, so from -2 to 6, and I counted by 1/2. So then I went ahead and graphed, and we can see here we've got a nice intersection point, and we want to find that x value. So we'll just do our intersection. So second calc, intersect. My first curve is the blue one, my second curve is the red one. I make a guess, and we get about 60.85 years for that material to decay to less than 1 gram. In the next sample problem, we're going to explore compound interest. There are 2 compound interest formulas. There's one for when you're getting compounding per year, the number of compoundings. So compounding is when your interest earns interest, or when the investment, they take your earnings and they add it into the principal so it can continue to earn additional earnings. So your interest earning interest, if you will. So the more compoundings there are for you, the more times they add the interest to the principal so it earns more interest, the better off you are. So you prefer to have monthly compounding as opposed to annual compounding. And daily compounding is even better than monthly compounding. But what's even better than daily compounding is continuous compounding. So that is a formula that involves our constant E. So here are two formulas for compound interest. You will have to make sure you've got your data here, but our ending amount, A sub t, equals P. P is our principal, or the amount that we invest, is the P. That's our investment amount. And R is the annual interest rate in decimal form. So 7% would be 0.07. N is the number of compoundings. So if you're getting something compounded monthly, it would be 12 compoundings, or quarterly would be 4 compoundings. So those are the different N's. Weekly compounding would be 52 compoundings. So you'll need to be able to keep those letters straight and what they represent. In continuous compounding, P is still our principal, R is our rate as a decimal, and T is time, or for how many months or years we're compounding. So in example 10, suppose you win a writer's competition at the start of the 9th grade, I guess that's supposed to be, that deposited $5,000 in an account that pays 6 1/4 interest, compounded continuously. So we are going to use number 2, the continuous compounding formula, or PERT as I like to call it. How much will be in the account when you enter college 4 years later? So our T here is 4. So we want to know our ending amount, A sub t, or if you will, A sub 4, equals P, our principal amount, $5,000, times E to the R, our rate is 6 1/4, so 0.0625, times T, or times 4. And we can go ahead and put that all into our calculator, and A sub 4 is $6,420.13. And we'll get some more practice with compound interest and growth and decay formulas when I see you in class.